This is video 4 of topic 11 on climate change. This video focuses on carbon dioxide concentrations and carbon emissions. To this point, the videos have described the natural greenhouse effect. In other words, the atmospheric warming that makes our planet habitable, with an average surface temperature of about 15 degrees Celsius. There are, however, a number of anthropogenic sources of gases that are enhancing this greenhouse effect and warming the planet further, which is really the topic of our section here on climate change. The principal gases, as we've seen in previous videos, are carbon dioxide, methane, nitrous oxide, and halocarbons, as well as some aerosols like black carbon, or soot. Carbon dioxide has been recognized as an important greenhouse gas for over a century now. In addition to some of the other sources that we've learned about for atmospheric concentrations of gases, there have been continuous, precise, and direct measurements of atmospheric CO2 since 1957 in Antarctica and 1958 in Mauna Loa, Hawaii. They've been collected by a scientist named Keeling. To put the values in context that you're about to hear, consider that over the last 800,000 years, as we know from ice cores, values for atmospheric CO2 concentrations have ranged from about 180 to 280 parts per million. The first direct measurements in 1958 showed atmospheric concentrations of about 315 parts per million of CO2, with a low growth rate of less than about 1 part per million per year. NOAA started with a network of sites in 1979, which allowed them to calculate a global average value for the CO2 concentration. In 1990, the value they found was 354 parts per million, with a higher growth rate of about 1.6 parts per million per year, and by 2006, the value was 380 parts per million, with growth of 2 parts per million per year. Currently, the value stands at over 415 parts per million. We reached 400 parts per million back in May of 2013. To put this number in context, during the Middle Miocene, about 14 to 10 million years ago, temperatures were about 3 to 6 degrees warmer, and the sea level was 25 to 40 meters higher than at present, and at that time the partial pressure of CO2 appears to have been similar to current levels. This is from Science. If you want more data on atmospheric CO2 levels, you can check these two sources. They provide lots of information. Interestingly, the NOAA data show annual oscillations in the CO2 levels. You can see them here. It's a sort of sinusoidal curve. These are seasonal variations in the rates of photosynthesis and respiration. And so, in a very real sense, the planet breathes through photosynthesis and respiration and decomposition. The levels of CO2 begin to drop in the spring and summer, and then they reach a minimum in the northern hemisphere in October when plants begin to hibernate for the winter. And this is caused by photosynthesis. Here you can see there are 6 carbon dioxide molecules and 6 water molecules, and with sunlight and chlorophyll they produce glucose and oxygen. And then respiration and decomposition reverse the process in the fall and winter and return carbon to the atmosphere. And so here you can see the glucose being broken down with oxygen, and it produces again CO2 and water and energy. This is what the cycle looks like over a longer period of time. So this is the instrumental record from 1958 onwards. You can see the pretty significant rise here, and notice that it is unfortunately exponential, so it's accelerating. You can also see those annual cycles, the sinusoidal cycle. This is from Scripps again. We've learned about the hydrological cycle in this course. There are many other cycles in nature, of course, and one of them is the carbon cycle. So carbon continuously circulates among the atmosphere, the terrestrial biosphere, and the oceans. At any one time, the atmosphere contains about 770 gigatons of carbon, and for reference here, a gigaton of carbon is a billion tons, or 10 to the 15 grams. The biosphere contains about 2,300 gigatons of carbon, and the oceans contain by far the largest amount, which is 38,000 gigatons of carbon. This figure here shows reservoirs of carbon in the rectangular blocks, here, here, and here, and then it shows fluxes or flows of carbon between these reservoirs in black for the natural cycles and in red for the anthropogenic effects on the natural cycles. So naturally, the atmosphere is assumed to have held about 597 gigatons of carbon, and we've added about 165 to that. There's more information here, of course. Now, in comparison to the natural fluxes of carbon, the additional amounts from combustion and cement production and land use change and so on are fairly modest, but they are large enough to have an effect, and that's the key point. According to figures for the 1990s, fossil fuel combustion and cement production released about 8.5 gigatons of carbon per year. Reforestation, accelerated plant growth through CO2 fertilization, and oceanic uptake removed about 5.3 gigatons from the atmosphere each year, and that left about 3.2 gigatons of carbon in the atmosphere. This is called the airborne fraction, which is about 38%. This is what it looks like. So here's the fossil fuel and cement production, here's land use change, here's the net gain, and then here's land uptake and oceanic uptake. Energy use releases carbon dioxide and other greenhouse gases to the atmosphere. This is through the combustion of fossil fuels. China is currently the largest emitter. It surpassed the United States in 2008. The US is the second largest, but by far the largest per capita. And Canada is about number 8 on the list, between 8 and 10. And we emit about 32 million of the 7 billion gigatons of carbon. Here's a figure that shows the global CO2 emissions per region from fossil fuel use and cement production. These are figures from about 2010. Okay, here you can see various different nations, and then you can see the increase for some nations in CO2 emissions and the decreases in some other nations for CO2 releases from 1990 through to 2012. The blue indicates here developed nations, and the greenish indicates developing countries. This is according to the Kyoto Protocol classification of nations. Here's a more recent figure. This one shows the annual total CO2 emissions by world region. This is from Oxford University, their Our World in Data series. You can see 35 billion tons of CO2 now rather than carbon. To show the previous slide a little bit differently, this image shows who emits the most CO2 at present. You can see it's by far China that emits the most. About 27% of the global emissions come from China, and about 15% now come from the United States. Europe is a little bit of a smaller part of the pie. It's about 9.8%. Russia is 4.7%, and so on. So you can take a look at these figures in more detail. This omits an important part of the story, though, which is who has contributed the most to global CO2 emissions over the industrial period of society. And if you look at it this way, the United States and Europe are responsible for the majority, 25% and 22% respectively, and then China is responsible for about 12.7% of the total emitted so far. So currently it emits the most, but if you look at it on a historical basis, the United States and Europe are larger emitters. Per capita emissions are also revealing. Again, China looks rather bad on a national basis, but if you look at per capita values, North Americans consume by far the most, 17.6 tons of CO2 per person per year, as compared with Asia, which is about 3.8 tons of CO2 per person per year. And the cumulative emissions, as we saw in the previous slide, are important. So which nations bear the most blame for the current rate of climate change? Well, you can see here, it's a comparative graph. You may be interested as well in where those emissions actually come from. Most of them are tied to energy use. So here's the sector that uses energy. Here are industrial processes. Here's agriculture, land use change and forestry, and waste. Here are the different end uses or activities that are associated with this energy use. We have here industrial and you could say urban, I suppose, uses. So road, buildings, fuel combustion, iron and steel production, chemical and petrochemical production, and so on. Agriculture produces livestock and manure, and rice cultivation is also responsible for a fair amount of emissions, as are off-gassing from agricultural soils, so the decomposition of organic matter within those soils. And then for land use change and forestry, we have burning, forest land clearing, and cropland. And then for waste, we have landfills and wastewater treatment. And then the types of gases they produce vary. So for the energy sector, it's primarily CO2. For agriculture, it's almost entirely methane and nitrous oxide. And then there are some halocarbons down here as well. An important concept is the carbon intensity of fuel. The carbon intensity is the amount of carbon that's released per unit of energy produced. It's usually measured in something like, say, grams or kilograms of carbon per megajoule or gigajoule. Some fuels have a high carbon intensity, like coal. Others produce no carbon, like wind or nuclear power. Biomass fuels release carbon on burning, but they also store carbon as the plants grow, and so it's said that they produce a net release of zero. No energy sources actually have zero emissions because of the manufacturing process. So even solar cells and wind turbines require some fossil fuel production or some fossil fuel consumption to produce the windmills and photovoltaic cells, for example. You've seen both of these terms now. It's important to know that they are different. So gigatons of carbon are not the same as gigatons of carbon dioxide. The conversion factor is just based on molecular weight. So 1 gigaton of carbon is the same as 3.67 gigatons of CO2. And now here are three major fossil fuels. Here's the low amount of carbon released for every megajoule of energy. Here's the high amount. And then here are the global emissions in gigatons of carbon per year in 2005 compared with 2018. And note this definition down here. Low and high values are more often called actually the higher heat value and the lower heat value carbon intensities. Okay, so take a look at these definitions. What I want you to notice too is this is 13 years before this value. The emissions at that point were about 7.62 gigatons of carbon. By 2018, 13 years later, 9.43 gigatons of carbon. That's an increase of about 24%. As you've seen on the previous slide, natural gas is preferable since it emits the least carbon per unit of energy produced. However, most of the world's fossil fuels are actually in the form of coal, about 90% in the United States, the former USSR, and China. The figures you'll see in the table below are from 1996. They're still deemed to be fairly accurate. The conventional resources are the types that we currently exploit. The unconventional resources include oil sands, Devonian shales, and coal seams. And then there's another column called additional occurrences. These may not actually exist, and they have unknown economic importance if they do exist. We may be able to extract them, we may not be. And so here they are. Here are the conventional resources for natural gas, petroleum, coal, and then totals in exajoules. Here are the unconventional resources and the total resource base. So that's the sum of these two values. And then additional occurrences are basically guesses. The carbon intensity factors on slide 55 suggest that conversion from coal to natural gas would reduce CO2 emissions significantly. Efficiency also plays an important role. For example, if we switch from coal to natural gas, this would possibly reduce our emissions by as much as 41% and deliver the same amount of energy. Here's an example. First of all, estimate the increase in atmospheric CO2 if the 125,500 exajoules of coal were to be burned. Assume a constant airborne fraction of 38%. We can first estimate the carbon content using the lower heat value from table 8.3. This is the one I termed high. So then this is 125,500 exajoules times 25.8 grams of carbon per megajoule times 10 to the 12 megajoules per exajoule times 10 to the minus 15 gigatons of carbon per gram of carbon is equal to 3,238 gigatons of carbon, which is roughly 4 times as much carbon as currently exists in the atmosphere. Converting this to CO2 and including the 0.38 airborne fraction gives us the same number here multiplied by the airborne fraction over a conversion between gigatons of carbon and parts per million in the atmosphere of CO2. The change in CO2 would be 580 parts per million of CO2. That would result in 2.5 times as much CO2 in the atmosphere as we have today. In fact, it would likely be higher than that if the airborne fraction increases due to the ocean ceasing to be such a good carbon sink. So you remember they held 38,000 gigatons of carbon. This is because they soak up CO2 in the atmosphere. If they stop being an effective sink, then we can imagine this value would increase even further. Note that if we burned all the oil and the natural gas, that would be a less significant factor. It might add about a third more CO2 to the atmosphere. I mentioned that efficiency matters. Here's an example of efficiency effects. The question is, compare the carbon emissions to heat household water using the following 3 energy systems. 1. A very good 37% efficient coal-fired power plant delivering electricity to a 100% efficient electric water heater. 2. A new 50% efficient natural gas-fired combined cycle power plant for that same electric water heater. And 3, we're going to bypass the electricity production entirely. We'll just have an 85% efficient gas-fired water heater. Assume that we have 6% losses in the electrical transmission lines as well. Here's the solution. Let's base our comparison on 100 megajoules of energy provided to each system. Using the lower heat values given in table 8.3, which again was on slide 55, burning 100 megajoules of coal releases 2,580 grams of carbon, while 100 megajoules of natural gas releases 1,530 grams of carbon. As suggested here, the coal plant system delivers 100 times 0.37 times 0.94 is equal to 34.8 megajoules to heat the water. The more efficient gas-fired power plant delivers 100 times 0.5 times 0.94 is 47 megajoules to heat the water, and using gas in the water heater delivers 85 megajoules of heat. Schematically, here are the first 2 examples that have the electric power plant. We have 100 megajoules of coal burned. The plant is only 37% efficient, so it produces 37 megajoules of electricity. We have some losses in the transmission line, so what gets delivered to the home is 34.8 megajoules. And then we have the electric water heater, which consumes 34.8 megajoules. And recall that to get this energy for heating the water, we had to release 2,580 grams of carbon. And so for every megajoule of energy, there are 74.1 grams of carbon produced. For the natural gas case, we have a better efficiency, and so we get 47 megajoules delivered to the home. And we also have lower releases of carbon from natural gas burning, and so our final value is 32.5 grams of carbon per megajoule. The case where we bypass the electricity plant entirely is the best, however. So here we have 100 megajoules in natural gas delivered to the water heater. It uses 85 megajoules of that to produce hot water. And so we're only producing 18 grams of carbon for every megajoule if we bypass the electricity. As you can see then, the carbon intensities for each system are shown in the figure. Switching from coal to gas in the power plant reduces carbon emissions from the electric water heater by 56%. Using gas directly in the water heater reduces carbon emissions by 75%. which is much more than the 41% improvement that I expected based on just the carbon intensity of natural gas versus coal. To wrap up this video, let's look at the implications of different climate policies on global temperatures. Here are global greenhouse gas emissions and warming scenarios. Again, the annual global greenhouse gas emissions are here, and the timeline is here. So we're going out to 2100. This is a case where the world does nothing, so no climate policies. We're looking at between 4 and almost 5 degrees Celsius of warming. The current policies that countries have adopted may lead us to 2.8 to about 3.2 degrees Celsius. The pledges and targets that are associated with the Paris Agreement, for example, could take us to 2.5 to 2.8 degrees Celsius warmer. And then this is what a 2 degrees Celsius pathway actually looks like, and a 1.5 degrees Celsius pathway. You'll note that the 1.5 is actually not net zero, but actually below zero emissions. This ends video 4.